Thank you so much for coming here today. My name is Adi. I work on an open source project named LakeFS. Has anyone here heard about LakeFS before? No, it's a relatively new open source project. It's written in Go, and it's built for data engineers and data practitioners in general. So today we're going to talk a lot about data engineering and chaos engineering, and how can we combine these two worlds in order to create resiliency and trust in our data. So who here worked with data in the past? Data practitioners, data engineers, data scientists? Data scientists? No, okay, all data engineers, that's amazing. So let me take you back to a place in time where you've been working on an ETL, a data pipeline, legacy data pipeline, and you're tasked with replacing one of the logics. And it's a pressed, and you have to get the task done within a couple of days. It's a legacy code. Testing is like, sort of okay, but you can't really trust that what you're developing is going to work well in production on the scale that you're looking for. Has anyone suffered from this issue? Or they needed to replace a legacy code in their ETL pipelines, and it was very hard for them to develop trust in their own code? Like, does it really work? And there's a really good explanation for that. A lot of our distributed systems that we work with, distributed computing, are actually doing a lot of unexpected things under the hood. So a lot of the operations they're doing are not deterministic. They're stochastic, which means statistically it's going to do what we think it's going to do. However, most of the cases, we cannot really know what is going to happen. And this is a really good example. Holden is one of the PMC members for Apache Spark. She's contributing to this project. And she always talks about how hard it is to test Spark jobs. Has anyone here works with Spark, Apache Spark? Cool. Airflow? Iceberg? No? Okay, cool. So Spark recent version actually introduced more complexity into how the distributed computing works. And the reason they introduced complexity is because they want to optimize the queries that they're running, their distributed computing query that they're running. So what happens during the query, what used to happen, it used to do it statically. So it will compute the whole query plan, and then we'll get it, and then we'll run it. But now it actually changes the query plan on the fly according to where the files are, what is the partition, and the metadata. So it even introduced more complexity into the query plan that really emphasized the unexpected things that happens with data. And so we always think to ourselves, like, what can go wrong, right? And when we're looking at S3, which is usually our main data lake when we work with a large set of data, it gives us great consistency today, as of today, right, for a single file-by-file basis. So if I want to work with a specific file and I want to have strong read after write, I have that today. It wasn't the case a year and a half, 2 years ago. Well, now I finally have it, but the challenge is usually when I work with a large set of data, it's not only one file. Usually my table is going to be split over 1,000 files. 10,000 files. Usually I'll work with Parquet, or I work with Orc, or I work with Avro. And that means that I'm loading it as one table, or I'm loading multiple tables, but actually the representation on the disk on my file system is multiple files. So this is one of the challenges we have with S3 when we're running distributed computing on top of it, because it doesn't give us the consistency at the directory level, which is really a pain point when we work with distributed computing. Another challenge that we have with S3 today, it was built as a key value store. So there's no storage optimizations built into it. And this is by design, because it needs to be scalable, it needs to be easy to use, it needs to be a tool that everyone can leverage and start working with. And so many times there's the challenge of small files when we do analytics and machine learning, because it takes longer time to load that data. The more data the more files we need to get access to, the longer it will take for the operation to take place. This is just physics. And another aspect of what can go wrong with data flows is actually the infrastructure that we use to run these data flows. So one example is EMR, and this morning my EMR cluster decided to stop working, which is great. Terminated with failures. But there are more challenges to the EMR. EMR gives us an Hadoop environment to run different Hadoop applications. So a lot of times we want to do optimization to the cost, and so we want to default into spot instances. And spot instances are basically instances that can go up and down, and we get it at a relatively low cost. And a lot of us are using it and want to use them because when we're getting our EMR cluster up, we want to get the steps or the job done, and we want it to terminate at the end of the day. However, sometimes the spots AWS are actually killing some of our spots because there's some optimization. They need instances for other compute, etc. So that caused the cluster to fail, and that can be disappointing, especially if you're serving that results to your data customers. Another aspect sometimes is a challenge that we need to take into consideration is we want to upgrade our EMR version, or we want to upgrade only pieces of our EMR release. And many times it's coupled to a specific version. So if I want to upgrade my Spark, for example, but I don't necessarily want to upgrade Hive, or I don't necessarily want to upgrade my Hadoop to Hadoop 3, it might be that I won't find a dedicated release for these upgrades specifically. So that requires me to do a full upgrade and a full migration and a full testing for everything that I need, which can be really, really hard. So what more can go wrong with data, putting aside the infrastructure that we have? So there's also data components that can go wrong in it. So new component logic, very hard to test. We don't know what we don't know. Introducing new data sources, again, can be latency, late arriving data, not exactly the schema that we expected. So introducing incompatible schema changes can also create a lot of friction. Spark jobs can be running a couple of times accidentally, and so they might create duplication of the data itself. If we want to change, so if we're looking at data many times, we'll have multiple tables, and there's going to be some relationship between these tables. So if you want to change the table relationships keys, that requires full testing of what is happening, and also making sure all the data that gets in are actually complying with the changes in the relationships. And it can be that I wake up in the middle of the night because I'm on call, and I need to fix some of the rows. I have some problem. I notice some nulls, and I accidentally deleted all of yesterday's events partition. True story, happens. Another aspect of it is data duplication, which is very easy to create when we're dealing with distributed computing. So how do we gain confidence in the code that we create? Any idea? By tasting it, yeah. By destroying it, okay. This is another option to gain confidence. So a lot of what's happening in our ecosystem basically is YOLO. I don't know if you heard about that culture. It's like, you only live once, just push to production. Who knows, right? It's going to be okay. We're going to lose a customer. Someone is going to be upset. You're going to get that call in the middle of the night. Customers asking questions. It's okay. That's part of life. So a lot of engineers actually took the disagree and commit culture another step forward and said, okay, I have flaky tests. I cannot really trust my test. And so I disagree with the failing test, and I commit the code anyway, because I can't really gain the confidence that I want at this stage. Although I have unit testing, integration testing, system testing, end-to-end testing. And all of these are not enough when we work with a large scale of data. So today, this is what we're going to talk about. We're going to talk about how can we borrow a lot of the concept, or all the beautiful concept in chaos engineering and, that were developed by Netflix into the world of data engineering. So how can we really build the confidence in our data systems that's going to help us push to production without being afraid of what's going to happen, and also, hopefully, with less customer churn. So chaos engineering, the high level, speaks about 4 different principles. A is defining a steady state. And defining a steady state, this is our happy place. This is what we want to see. These are the requirements. Second thing is acknowledging that real-world events are not going to be a happy place. Knowing that, understanding the psychology of that, accepting it, managing the risk. Third one is how can we make sure we are aware of all the real-world events and we're building the system to support the real-world events. So this speaks about running the manual experimentation that we want to do in production. So testing in production systems. And the next level is now that I know how to do manual testing on my production system, I want to automate that process. Because I want to constantly remove the weaknesses in my system. I want to constantly be able to strengthen my system so I have confidence in it. And let's break it down for a little bit to see how these two worlds correlate. So steady state, when we talk about DevOps or SRE, or sometimes it's called IT, usually we'll speak about the system throughput, the error rate that we're getting, the latency percentiles, all of these aspects of the bare metal in the machine and our network. Steady state for a data engineer will mean data product requirements. At the end of the day, if we're building data products, we're selling data products, or we have internal customers for our data products, we need to know what are these requirements and hit them. Because it's not about the technology. It can be beautiful, to talk all day about Spark and what's got update there and the distributed computing and all the great engine. But at the end of the day, it's what Spark gives me and enables me to create the data product that my company sells. And data product requirements can be a bunch of things. But if we really distill it down to some of the recurring requirements, we usually talk about data quality. And the importance of data quality is, again, I want to trust the people that I'm selling the product to needs to trust my product. We're talking about accuracy. How accurate is my data product at the end of the day? Some requires no duplication, and that really depends on what system I'm building. And my SLA, how fast do I need the data? What is the refresh rate, etc. And you're probably curious how easy it is to create data duplication. So here is 3 rows of code, which creates data duplication. Take it a second to read and raise your hand if you're seeing why there's data duplication in it. This is a Spark code. It basically reads some data from Parquet, assuming we have some bank transaction that we're processing with some timestamp, and then it does some transformation, and it writes it back to the storage. And this mistake, yeah, I can see your hands up. Thank you so much. Do you want to go ahead? Yes, because it appends. Exactly. It won't do overwrite. It does append. And this happens frequently because sometimes we miss on exactly what it is, the function that we're doing. We're not really connected to the path that we just used. Or we're doing some backfilling and accidentally doing append instead of overwrite. So it's very easy to duplicate code, and it's very hard to test this duplication often. So the second value is acknowledging that there's going to be real-world events that we cannot control. The larger the scale, the more events are going to happen, and that's fine. So from a DevOps point of view, is servers dying, spike in traffic, trends, things that we couldn't predict, etc. From a data engineer's point of view, it can be the schema that got changed, corrupted data records that got into my system, data variants that I didn't expect, or I accidentally deleted production data because I was on call and things happened. And so I deleted it, and then my weekend is fun, basically. The third principle speaks about running experimentation in production manually. So here is where a lot of the work of Chaos Monkeys gets into place, or a step before Chaos Monkeys actually, is actually killing some of the machines ourselves and see what happens, or create a spike in the network and see what happens. And for us, it's running our logic on production data and see what happens, right? And so when we want to run our experiments on our code or testing on production data, In data engineering, we already developed a system for that. And this system is called copying the data. What we do, we go to S3, and we're just copying massive amounts of data. Now, S3 is relatively cost efficient, right? A lot of people here are using S3, I'm guessing, right? Everyone is like one of the basic aspects of working with data. So we're copying it. It takes some time, especially if you're working with a petabyte scale size. But we're copying, we're testing. We can understand if our logic does what it expected to do. We can do some difference, some computation on top of it, and merge it back. So we create this special path that's saying this path is for my specific experiment that I'm running on. It's great, it works. And now the next level is automating this experiment. So Chaos Monkey actually enables us to automate killing some of the machines, playing with the network, seeing what really happens. In the data engineering point of view, we don't really have automation to play with the data and really understand what happened and introduce bad data into the system. And so we have to develop a new concept or introduce a new concept of the data lifecycle and what happens between these different stages of the data when we are testing our logic on our production data, on our copies of our production data, etc. So what do you think the best way to automate creating data for testing, environment, and production data? Are we happy with copying everything a couple of times for every new logic and everyone in our team? Deep copies. I mean, S3 is cost efficient. Yeah. Yeah. Yeah, introducing backup or snapshots in databases, sometimes we call it in the database world. Yeah, this is what we do as data engineering, where we have our staging environment and we're mirroring the data or snapshotting the data into our environment, and we create some automations around it. So it works. So I want to call it in a slightly different name than snapshot. I want to call it branching. And branching is a concept that we know from source control. When we work with software, we have our Git. And when we work with Git, we have our main branch. And then we're branching out. We're introducing some changes. If we're happy with the changes, we do some testing. We can merge it into our main branch. Or we can roll back, right? If we're not happy, we don't know exactly what happened, we can do everything that we want and make a decision and, do a commit and roll back to a specific commit, etc. So this is a relatively new concept for working with data, the whole aspect of branching, but definitely something that we can think about when we decide to work with a large scale of data, because we are doing copying, and it's very similar to how we used to work with software before we had Git. So that brings us to Git for data. And Git for data enables us all the solutions that Git gives us. And so when we think specifically about the challenges is when we have some data in production and we introduce some error either in testing or not in testing, we're able to revert. We can roll back from this specific error that we just introduced to the system and go back to a release of that data, a promotion of that released data that is in a good state. So if I have a customer incident, I accidentally delete one of my customers' data, instead of wasting all my weekend, I can roll back to a stable version of that data and then get back to it on a Monday. Right? That enables me this comfort as a software engineer, as a data engineer, to handle the problem and to troubleshoot the problem with comfort. It also enables me to develop in isolation because I have my own branch. Now I can run my experiments, I can run my testing, I can do everything that I want on top of that. So that gives me the automation, the automated testing environment that I so want and need in zero copy mechanism. Because Git models specifically under the hood, it uses a zero copy mechanism. So similar here with working with data, it uses a zero copy mechanism. So it gives me the isolated environment without having deep copies of all my data. So I can do that, and I can troubleshoot, and I can go back to a specific commit. I can do atomic updates, right? Because now I already have a specific branch. So if I'm doing my update, I can decide if I want to merge. And this is one of the challenges we spoke about when we started about S3, right? I have consistency over a file, but I don't have consistency over a directory specifically. And I can reprocess. I introduced some logic into the system. I'm not happy with this specific logic. So I can roll back to a specific version, introduce new logic, and then reprocess it. So the Git concept and the Git idea gives us a lot of opportunities to solve a lot of deep problems we have when we work with data that we solved using copy. Not to talk about if you have PII in your data. If you are doing deep copies of all this data, that means you have to manage it somewhere. You have to do something about it. You have to encrypt it. Good. So this is where LakeFS comes to play. So LakeFS is an open source project. You can all go to GitHub and find it there. And LakeFS brings a lot of the Git concepts into the world of data. And also the versioning engine behind it is built very much like Git. So it does hashing of the file, so it knows what got changed, and it only holds pointers to where the files are and the hashing itself. So it's very low weight. It only holds the metadata. And it builds as a client-server architecture behind the scene. So this is just one example. If you can imagine that you have your main data pipelines run in production, and you want to branch out and try some logic over your dirty ingest branch, for example, because you're now introducing a new logic of ingest into the system, LakeFS enables that for you. You'll have an isolated environment where you can test introducing this new ingest branch and decide if this logic is good for you or not, and then you can release the new version of your software with confidence that it works. On write, yeah. So if I have my commit and I created a new data, yes, on write, it will hold the copy specifically for the file. But if I'm only reading and doing some processing, and I'm not writing to that specific file, I'm creating a new file, or I'm enriching some tables that I do a lot with analytics, enriching tables and join, then it's a different mechanism. And we actually tested it statistically. Only 20% of the data is actually being changed. So a lot of people load all the data that we have, even in big data space. But actually, they're doing a lot of extrapolation, a lot of computation on top of that data, which is heavy. But only 20% of the data is actually being changed. So yeah. The hashing mechanism also helps you when you want to merge the different branches, right? Because we want to know what got changed. If nothing got changed, I don't want to write files that didn't change. Okay. If I have a main data set, yes, I'm branching out. If I have more integration constraints from infrastructure point of view or from... So there's a merge strategy, and the merge strategy actually asks you as a user, who do you want to trust, the main or the branch? Or there's a source and there's what got changed and where you're merging to. So the merging strategy is going file by file and telling you, if I trust a new branch, then it will override what exists in your main, for example. And this is a great question because it also means how do I run my quality assurance on top of the data, right? Which is a critical aspect. So if I'm deciding to merge and promote my data into production, and I'm saying this is in a good state, it can be used by my data customers, I want to test it, right? And LakeFS also provides that out of the box. There is a webhooks mechanism. You create a server, and you hook it together with LakeFS. You use a specific tag, so you can actually test your branches using that mechanism. It's an infrastructure mechanism. It doesn't come with the server for the hooks and the yeah. Is there? So the question was, and because for the recording, is if there is a merge, if there is a update and delete that happened inside my branch and I want to merge it back, would there be a conflict with the main branch? So this is why the strategy asks you as a user, who do you trust? Do you trust the new branch that you just created? Is that the data that is the source of truth, or do you trust the main branch? And so according to the user, this is what the merge is going to do. Yeah. Yeah, so basically you can create the dev experimentation branch and write the commits and collect the logs and decide what you want to do if you're happy with your logic. So just a quick sum up, and we have some more time left, right? Yeah. 10 minutes. 8 minutes. So the goal of this project, open source project, is to really learn from what exists in the SRE and DevOps and IT world so we can adopt the principles to data systems, because we have a lot of challenges, a lot of friction with data system today. And so we offer branching strategy instead of copying the data ourselves or creating scripts to copy the data. And so Git for data really makes sense when we're thinking about branching strategy. And LakeFS is an open source project that is loved by the community and is being used and tested in various companies. I did create a demo. My EMR cluster is not happy with me today. So I apologize, but I have another one just in case. And because we have a couple of minutes, so this is a LakeFS instance that runs on AWS, on EC2 specifically. And this is how it looks like. I have my repository similar to how I have with Git, so I can actually go in and see what exists and what are the different, what I have here. So I can act as like every ETL can be its own repository that looks into, that directs and has pointers into S3 files. And within that, you can see the different branches. So I have, at the moment, I have only a main branch. And I can either create a new branch using the SDK, which was I'm going to show you, or I can do it from the UI, or I can use the CLI as well. So here, I created a Databricks environment just in case. And inside the notebook, I am creating a LakeFS client because, as I mentioned, it's a client-server architecture. So I'm taking the clients, let's assume it's a Spark job that I'm going to run, and I can list all the branches that I have using a Python function. And it's going to return back, you only have a main branch, because this is where we're starting at when we want to test our logic. We really want to see what's happening. So we only have a main branch, and now we want to create a branch. So the Python SDKs enable me to create a branch. I'm giving it a name, and I'm calling it experiment chaos. Some chaos that happens in the system, and the sources comes from my main. Setting some variables, running diff in between the branches to see what file got changed. My diff is empty because I didn't do anything yet. Loading the data from the specific chaos repo path. So as the path changes, now it's not slash the path specifically, but it's slash main or slash chaos repos that I have. For the two tables that I have, so I have genres and I have books. And just to give you a gist of what exists in this book, because it's fun. If you all love O'Reilly books, I'm a big fan of O'Reilly books. We have some great authors here as well. So some fun O'Reilly books from great authors in the ecosystem. So one table is books, the other one are genres. High performance yarn, genre fiction. If anyone here has worked with yarn, it will resonate with you. Or Intro to Hive Metastore. It's a mystery story. If you ever looked into the internals of Hive, it's a lot of fun. And yeah, Life After Hadoop, it's a crime. Yeah, just my brain. Creating the tables, saving the tables. Again, Hive operations here inside this notebook. But what I want to show you, the join operation. So join operations takes some data from books and genres and does the join on the ID, the ISBN. Specifically in books, it does a left join. And a left join can introduce nulls, and this is by design I'm using it. Because when you're thinking about specific tables, you usually have all these wonderful Venn diagrams that everyone forget what they really do. Some of them introduce challenges, so I'm just stating it out there. It's part of the demo. And we want to save the materialized view that we just created. So we're saving it under the repository. What I have now is this materialized view of the two tables together. And I can already see, because I used the wonderful join, that it introduced nulls into my data. And that happens all the time when we work as data engineers. And usually we use two techniques to avoid nulls in our data. One, we drop the rows. We lose data. Statistically, it might mean that the quality of our data product at the end can suffer from it. Second technique is default values, which again, statistically can harm the quality of our data product at the end of the day. And so I want to run some quality checks, and this beautiful function is going to tell me how many nulls would I have in my data set, in my new data set that I just introduced, because I want to know if my logic is good, if it worked, if I accidentally did something that shouldn't happen, etc. And I can learn that I introduced some nulls into the author, the name, the ISBN, and I'm running some more testing on it. And now I can go here and look at my branches. And my code introduced this experiment chaos, new branch where I introduced null values to. So I can go, you can see my uncommitted changes, which is one of the beautiful areas, and it will tell me exactly which files got changed. And because I introduced bugs into my system and I don't want to have bugs there, I can revert back. So my experiment chaos now doesn't have any nulls in it. That's it. And I can go back to my code and try again. Try a different join. And I'm running that on top of my production data in an isolated environment that enables me to test everything that I'm doing. And this revert mechanism takes me back to a stable state of the data, which really gives me the confidence to develop the code that I want to develop at the end of the day. So I can do the second join operations and basically continue running with the demo. And here the second join should work better. Data. Yes, now I have no null in my data. I have confidence in my code, and I can deploy it to production. Yes, I can do diff on the branches. Yeah. Yeah. Yeah, I can do it from the UI. I can do it from the Python SDK that I have. So if I'm going back here, I can show you. We had, where's my function? So I have the list of branches, right? So I should have my new branch in here, right? There's the experiment chaos. And my diff branch. I need to refresh it. Oh, wait. Just making sure I wrote it into, oh, I didn't write it. Wait, I need to count, fix, mix data. Let me just write the actual data because it's now still in memory. And thank you. It was already in my demo. I forgot about it. Yes, so we can see actually the diff through code and program something that can work on top of it.